Now, we don't need to know anything about the Cavendish experiment. Gentlemen, this question appeared in the WACE exam in 2014. And this is one question where the perpendicular distance is a much better method of solving. So, Alex, you've got about 1 minute left, buddy. Bring it up to the front when you're done. Great, I can stop talking about it then. Remember I said approximately 90% of all questions, RF sine theta will suffice. For this question, just have a look at it. You don't have to write out the whole thing. This will appear on the OneNote. If you want to sketch very quickly the diagram, then please do so. Now, you've got the mass, you've got the distances. It says to treat the bottom of the bolt as the pivot. Okay, so if we treat the bottom bolt as the pivot, then the top bolt is going to exert a force, and we know that it acts, well, 2 lots of 4 centimetres. Okay, but here is the problem. Students that only were taught RF sine theta, don't draw this by the way, would have to do Pythagoras to find R, and then they'd have, so they do square root of 0.4 squared plus 0.04 squared, blah, blah, blah. They'd find R, right? Then they'd do a whole lot of trig to find the angle theta. Well, it turns out the extension of R is cancelled by the minimization of theta. But then they'd have to do the same for the center of mass. Have I got a code? Are we back? Yes. Thank you. All right. Then, please stop talking. I'm waiting for you to stop. Then they do a whole lot of Pythagoras to find a different R to the center of mass of the support beam, and then a whole lot of Pythagoras or trig to do that. That is wasted. It's just extra time. You would have spent 5 minutes on something that's only worth 4 marks, and you haven't even started the question. Here's all you need to do. Let's draw the weight force of the projector, and let's draw the weight force of the support arm, which is going to act midway along its length, in which case R perp is simply 0.45 and R perp is 0.5. Okay, we do have an R perp straight up for the clockwise moment. So what we have, the projector and the support arm, R perp weight plus R perp weight. It's there, it's given. The perpendicular distance to the weight force and the perpendicular distance to the weight force must be equal to the clockwise moment. What? How'd you get 0.5? Because the support arm, uniform horizontal support arm, is 0.9 meters long. So its weight acts halfway. Okay? So, we would go clockwise moment equals anti-clockwise moment. We would go 0.08 force of the bolt must equal 0.5 weight of the projector, which was 7 by 9.8. And then 0.45 weight of the support arm, 1 by 9.8. Solving force of the bolt gives 484 newtons into the wall. Okay? Now remember, that's just the perpendicular. It wants the horizontal force. When we considered the door, this is very similar to a door with the two hinges. We would know that obviously that top bolt is going to actually be pulling up and in. The bottom bolt would be pushing out and up, such that you get kind of the, your weight, force of your bottom bolt, force of your top bolt. But the question's just saying, calculate the perpendicular. Done. Simple. Okay? Now, then there was this question, explain quantitatively. So you actually had to provide an equation. Now, if I went back, I rushed this bit here, okay? But what we're looking for is that the force of the bolt is going to be R projector, weight projector, plus R support arm, weight support arm, over the radius of the bolt. So I'm just going to take, that's the equation that we're going to use to explain, oh, for God's sake. Close enough. So, the effect on the horizontal force as the projector. So this, it's not actually proportional to the radius. Doubling the distance of the projector will not double the force, because we've also got something else producing a counterclockwise moment. Okay, so it's actually proportional to R plus some other constant. It's not directly proportional to. Okay, however, to get full marks, you had to show the equation. Okay, and therefore, as R increases, force bolt increases. So just be careful. Lots of students would be saying, oh, as R is doubled, F is doubled. Well, no, it doesn't. Try it out. Throw in and double the R, you're not going to get double the force, because there's something else producing a counter-clockwise moment. This question is a lovely question, and 50-50. Half students might wish to do perpendicular distance and half students might wish to do perpendicular force. But this is a great question. Let's just throw in a few bits of information. We've got 0.15 meter step. The radius of our wheel is 0.55. All right, so if you want to quickly sketch this diagram, it shouldn't take you long. And there is a force that's acting horizontal from its center, and we have a weight force here, which is 80 by 9.8. Okay, so get that in for me, please. Now, if I wanted to find R perp to the force applied to the drum by the handle, that's not too tricky. It's just this distance here, which is going to be 0.55 less 0.15, which is 0.4. So that force is 0.4 directly upwards from the pivot. Okay? But this one here, this R perp, is a little bit trickier. It requires a bit of trick. We've got 0.4 on that side, and we've got 0.55. So I would say that Pythag C squared minus B squared gives A squared, and so I could find that R perp is 0.377. Okay? So that's the only bit of trick that we had to do there. It's just one. The student that wants to go down the perpendicular force method would have to, well, you'd have to find a theta, and then you'd have to find phi. Well, again, that's just one bit of arithmetic and one bit of trigonometry. So really, this question is equal amount of work or effort required to solve for this. Okay? And so it just becomes clockwise moment equals anti-clockwise moment. Our clockwise moment is going to be 0.4 F equals 0.377 weight of the drum. And so F is going to equal 745 newtons. Something to add? Yeah. Thank you. Next. Explain. What happens to the size of the force as the wheel rises? There's actually two things that happen. So I'm just going to imagine we took that circle and I'm going to try and draw it, it's rotated up a bit, okay, like this. That wasn't actually too bad. We're raising the wheel up. Two things are happening. We're actually reducing the perpendicular distance of the weight force to the pivot. So as you're pulling the drum up, it's the center of mass is coming towards the pivot horizontally. So we're reducing the perpendicular to the distance. But also, look at my dashed line now to the force. We're increasing the perpendicular distance to the force. Now, I can't recall, it is getting a little bit cool now, I'll turn that off for everyone. I can't recall the marking key. I want you to appreciate that both things are making the force decrease. We might have allowed students to pick one, okay? So you could say the counterclockwise torque produced by the drum decreases as its perpendicular radius to the pivot decreases. Therefore, the force on the other side must reduce. Also though, a reduction in torque, you also have an increase in R. So your force required is going to decrease by both effects. It's going to become much easier once you start lifting it up. Okay? And then lastly, calculate the angle above the horizontal the wheel can be pulled, minimum required force. Well, I'm just going to undo. I'm just going to undo that drawing of the wheel raising up. Essentially, I want to rotate this force around to some point where R_perp is maximized. Well, that's going to occur when R_perp is the radius, yeah? And so this would then require a little bit of trigonometry that we'd have to find that theta and then probably go, oh, that's phi. Theta equals 90 minus phi, okay? Or if you're a perpendicular force kind of guy, you would say, well, my line of action, maximum force when sine 90 equals 1. That would give you the minimum force required. Sorry, not maximum force. The minimum force is when theta equals 90. Okay, so I hope you can sort of visualize what's happening to this perpendicular distance. As we rotate that around, that perpendicular distance is eventually going to become the maximum radius that it can, which is from pivot to center of mass. Okay? Now, we need to continue on. Please make sure you're doing the practice tests and the Jankowski questions and the review questions. You've got plenty of resources. We've got to continue on with our topic. We can't just skip stability because it may appear in the WACE exam. It may appear in the mid-year exam. So could you please get to this next page? Now, this is just an extension of rotational equilibrium. So it's not like we're starting a new topic. We're actually sort of expanding on what we already know. Okay, so, it will assist us in the test tomorrow. Okay? We want to look at stability. Stability is basically referring to the resistance that an object has to toppling, or if you gave it a small displacement, would it fall back to its base or would it topple and crash? Okay? What we have here are three different scenarios where you'll notice the hand is moving this object the same distance, the same height above the base, and it's above its center of mass, okay? So in each, you're just taking an object and you're giving it the same displacement. What I want you to realize for the first diagram is that if you give it a little bit of a nudge, it will pivot. I actually need this lesson to screen capture because the other lesson didn't go so well. Thank you for your patience, guys. Let me just disconnect my Wi-Fi. So guys, just have a look at the first example on that left side. I want you to put a pivot on the bottom right corner. I'd like you to then draw the weight force from the blue dot, which is representing the center of mass. 3184. Okay, so I used to try to look after my devices and I don't want to just scratch the crap out of them. So, here's my weight force that I hope that you've drawn. You'll notice that there's an R perpendicular, but the force is still on the left side. And so if you allow it, it will fall back down because the weight is still producing a counterclockwise moment. It'll fall back to its initial spot. You would say this bloke is stable. If we go here, you might notice now the pivot, we're at a dangerous point here because the weight force is directly above the pivot. This is a point of unstable equilibrium. At this point, the torque is balanced. In fact, there is zero torque. The translational forces are balanced. But I need you to appreciate, this is not stable because the tiniest displacement left or right is then going to produce an unbalance. Not only that, as it is allowed to move, this unbalance will increase because the movement increases the perpendicular distance, which increases the torque, which increases the rate of movement, which increases the rate of increase of perpendicular. It starts to snowball out of control. That is unstable equilibrium. Okay? This poor little guy, again, we've now got a scenario where the weight force produces from the pivot a torque it's on the other side of the pivot, and so the torque has changed direction. Before, it would fall back to its base because the weight produced an anti-clockwise moment. Now, the weight force is outside the base. It produces a clockwise moment. So could you just please write a note down here? Okay, it will topple. Okay? And so, hopefully you've been looking at the diagram. We've changed a few things. In each example, you'll notice that the center of mass has increased. The dot that represents the center of mass at the start was quite low, and then at the end it was quite high. So what I want you now to imagine is if we move the object a tiny amount, the further up that center of mass is, the greater the likelihood is that it's going to go outside the base. Also, the narrower the base, the greater the likelihood that the weight force will act outside of the base. Okay? So it comes down to just basic geometry. If we just go over the page, please. So we've got stable equilibrium, where a tiny displacement it will fall back. We've got unstable equilibrium, where the tiniest displacement it would just snowball and fall wildly out of control. And then we've got neutral equilibrium, where a movement will cause it to simply slide laterally. And so you can get these different objects. A cylinder is a nice example because you can orientate a cylinder in 3 different ways for it to be stable. Obviously, the weight is inside the base. Unstable, the tiniest movement sideways would make the weight fall outside of the base. Or neutral, where if I give it a push, it'll start rolling. Okay? And you can do the same with conical shapes as well. So again, down here, won't topple, point of instability, will topple. I'd like you to consider these diagrams. What we need is a little bit of geometry. So our weight force, yes, if it goes through the base, then it is stable. Okay? If I wanted to rotate this object such that its weight force was directly above that pivot and get it to a point of instability, I would have to rotate it by the same theta. All right? That theta there, rotate by, and we get to that point. I hope you're not asking for a mathematical proof that our theta angle is the same. Okay? So, how could we design an object to maximize this angle theta? How can we make the angle theta bigger? Toba? Absolutely. Let's do that. Or let's not do it near the truck. Let's do it bottom left. So, what did you said? Increase the base. Absolutely. And so now, yes. What have we really done in mathematics? We've increased the adjacent side length, and so that angle would increase. So yes, a wider base will produce a more stable object. Think baby chairs. They have big splayed out legs with a wide base. Think bar stools. They normally have large bases. Yes?
With that diagram, is theta the angle from the horizontal upwards, where it's being tilted?
The angle to the angle between the weight force and the line of action, really. It's going to determine the magnitude of the torque.
But the base and the horizontal.
This bit here. Well,
the base and the horizontal, the floor.
It's the same angle. I don't know, Rahal. It's this one here with the angle symbol that I've drawn.
No, between.
Which is also that one.
Yeah.
Yes. Cool. Yes. Cool. It's been a long day. All right. What else can we change to make? Yeah. Go. Give me.
Bring the center of
gravity
closer to.
Good. Thank you. So let's go back to the same narrow. If we drop the center of mass down. Okay, then yes, what are we doing geometrically, we're decreasing the adjacent angle. That will also have the same effect. It will increase that angle. Okay? And I'm sure it's mentioned somewhere that we want to have a low center of mass plus a wide base that will increase stability. Okay? So, this is very important when it comes to stacking things in trucks. Right, your truck has a certain wheelbase, and for some strange reason we've packed so much junk into our trunk that the weight force is so high that it now falls outside. Oh, that's not really vertical. Let's try that again. Close enough. Okay. In this scenario, what could we say? We could say that phi is greater than that angle. Okay? Again, we could say that now the weight force about the pivot is outside the base, or the weight force lies outside the base. This produces this produces a moment on the other side of the wheel which would cause it to topple. Okay? So trucks, generally you don't park your truck on a massive incline like that because it's probably going to fall over. And also going around corners as well, which is a bit tricky because you've got weird forces there. friction pushing underneath, but anyway, we'll get to that. If you're going too fast around the corner, the higher the centre of mass, the more likely it is going to topple. So if we now consider a low, souped-up Formula One from the 1980s, when you were allowed to advertise cigarettes, in fact, it was even from the 90s, now the weight force lies within the base. So now if we consider a pivot, perpendicular distance occurs inside the base. I can't really draw this because or maybe I could, theta and phi. In this case, phi less than theta. Okay? One other way to look at stability, and this may have occurred with the person walking along the plank and that will it topple, is it stable? There's been a few of those questions in previous years' tests. Will it topple? Is it stable? Have a look at the Marlboro Formula One Ferrari. The weight force about the pivot produces a counterclockwise torque. Would you agree? Yes. All right. What do you think about the pivot? What is producing the clockwise torque to maintain rotational equilibrium?
Reaction.
Of which wheel?
The further up.
The further up wheel. Yes. The wheel here is going to produce a reaction force. Where's our perpendicular distance? Ooh, good question, Mr. Murray. Ooh. I'm not going to draw it on my diagram, but... Oh, wait, is it just that? Oh, I got excited by extending out my... Okay, you don't need to extend your force. So, yes, as long as the weight force is within the base, the outside wheel produces the surface of the road pushes on the wheel, okay? Follow my logic here. If we tilt this road, angle it more, bring that weight force now becomes closer to the pivot, the torque reduces. And so the reaction force on the outside wheel reduces. There will come a time, or an angle, where this becomes zero. At which point, there's no torque, so there's no reaction force on the outside wheel. Does that make sense? That is the point of instability. Okay? So if I had drawn this so that the weight force was directly over the pivot, then this outside wheel is not in contact with the road. A little 3-year-old could come up to the side of the truck and go, ha, 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 and push the thing over. Remember, the point of instability, the tiniest displacement produced by a 3-year-old is going to suddenly snowball effect, the thing topples. Okay? Some students brought... let's look at the Happy Sumo. We've got 5 minutes left. Happy Sumo. The rigid sumo. Now, obviously, sumo wrestling, and in fact any wrestling, if you wish to maintain if you want to stay upright and on your feet and not get tackled or toppled, you want to increase your base and lower your centre of mass. Alright, so you want to get nice and low and have a wide base. That makes you more difficult to topple. Okay? So our Happy Sumo is rigid. Obviously, if I'm applying a force to this guy, I don't want him going like that. Treat him like a block of concrete. Okay? Well, you have to. You treat him as a spherical chicken in a vacuum. Now, I've already set a pivot point here. Obviously, his weight force is over here. And so we have increased our perpendicular distance to the weight force. Let's just keep my weight forces in blue, sorry. And so 120 by 9.8, I don't know what that is, so I'll just write it 120 by 9.8. That's his weight force, okay? We know his RPerp is 0.7. So I know the torque produced by his weight. It's going to be 0.7 times that number, that's the torque. If we want to topple him, we have to produce a force greater than. So let's suppose we grab his hand and we yank it this way. Okay? You grab him and you're like, I'm going to make you topple. It's no longer a sumo wrestler, it's a statue of a sumo wrestler, so it's rigid. So now we've got RPerp up here as 0.9. Okay? So obviously the force required to topple to topple is a weird statement. It's basically now saying that in this diagram, your anti-clockwise moment is now greater than your clockwise moment. So we're no longer in equaling, we're not in equilibrium. I'm now saying, let's get this guy accelerating. Let's get him rotating, okay? So it becomes our so 0.9f greater than 0.7, 120, what? 0.9f, write this down, greater than 120 times 9.8. F must be greater than the torque produced divided by the distance that it's acting, must be greater than 915 newtons. I hope that's appearing behind me. Thank you. Okay? All right. So that's the maximum. This is assuming that he doesn't slide. If this sumo wrestler was on a skateboard and you grab him, you're just going to translate him, right? So what do we require to occur at the pivot? Friction. Yes. So, obviously, these are not the only forces acting on the sumo wrestler, or else he would be going down and left. Well, at the moment he's stationary. So there would actually be a reaction force on his forward foot, FR. Because remember, at that foot, give it about 5 seconds. There seems to be a 10-second delay. On that foot, if he's toppling, no reaction force. So really, at that point of instability, all of the friction and reaction force is at that lead leg. And remember, anything greater, and he topples, anything less, and we get a reaction force at his outside foot. Does it make sense? Have you kind of experienced this throughout your lives of wrestling your mates out on the oval? Let's just do one last activity. I know we've got 0 minutes left, but let's reduce it a bit. Let's set the force acting on that hand to 700. Let's go below, okay? So if I was to draw a very quick torque diagram, we've got 0.9, 700 that way, and then we've got 0.7 and 0.4. His weight force acts about there. But now, his outside foot is still in contact with the ground. And it's going to be 1.4 meters from the pivot. And it's going to produce a clockwise moment to maintain rotational equilibrium. Remember, we're not toppling him now. The person that's trying to pull him over has given up slightly. They've weakened their force to 700. So now the question is, what would the reaction force be? So, clockwise moment equals anti-clockwise moment. It's going to be 0.7 times his weight. And now we've got two anti-clockwise moments. 0.9 by 700 plus 1.4 FR. I hope you don't mind me going underneath. And so we subtract that, then divide by the base. We get FR equals 138 newtons. At this moment, this foot is still in contact with the ground with 138 newtons of force down, and then the floor pushes up with 138 newtons of force up. The last thing we could then do, up and up, you could do the translational equilibrium. Gets a little bit tricky because now coefficient of friction. I don't think it's too tricky. Maybe it's a ratio. The inside foot, which we can solve upwards, the outside foot upwards. I reckon it would be a ratio. I reckon if the inside foot was taking 80% of the upwards force, it's probably also taking 80% of the friction. Yeah?
In rotation to the rim, don't you have to consider like weird pivot points?
Well, if it's sliding, then we can't use the rotation about a pivot.
Yeah.
So there's everything. We're going back to static now. This was a static example. It wasn't sliding or rotating. Okay? All right, guys. Thank you for your patience.